there are two things that I want to go over today that have to do with this. And the biggest thing I want to start with is this is not particularly hard, um, but there are multiple ways to come at what they're asking you. The problem is that it deals with something that you guys don't really have a whole bunch of information about, and that's the mathematics behind an ellipse. Raise your hand if you took AP Pre-Calc. And is there anybody here who did take Pre-Calc honors? So you have an advantage, and it's a problem. We're simply talking about the idea that an object that's in a orbit, in an elliptical orbit, has certain properties, and that's what we're going to talk about today. And I really want to highlight the importance of these two places because they have certain special geometric consequences. These, not so much. So for just a moment, let's talk about the fact that the object's going to have its fastest velocity here. This would be the maximum speed of the object. And that's due to the fact that it's closest to whatever it's orbiting. So we're going to treat today that this is a planet and this is a satellite, and that's how I'm going to do this. But this could be a star and a planet if you'd like. It could be anything that's in orbit. Go halfway around the orbit over here. This is going to be where we have our minimum speed. We are the furthest away from the planet. So gravity is the weakest there, so its velocity is the least. And when you're closest, gravity is the greatest there and velocity is the highest. And of course, places in the middle are going to be somewhere in the middle, but remember, the velocity is always going to be tangent to the curve of the ellipse. And that's going to make points 3 and 4, or any other place that isn't point 1 and 2, somewhat geometrically complicated. And we'll talk specifically about what I mean by that here in just a sec. But there's two other relevant things you need to understand about an elliptical orbit. When you're in an elliptical orbit, let's pick position 1 for just a minute. This circle represents what a circular orbit would look like if you're at position 1. The reason why the elliptical orbit exists here is because you're going too fast at position 1 to maintain a circular orbit. So you fall outside the size of the circular orbit. So if you were trying to be in a circular orbit and you made it to position 1 and your speed of your spacecraft was too quick, you wouldn't be in that stable circular orbit. You'd be in a stable elliptical orbit defined by how much faster you're going. And there's a similar truth to what happens if you find yourself all the way out there at position 2. There's a circular orbit that you could attain if you were at position 2. But to attain that orbit, you would have to be going faster than how fast you're actually going when you're at position 2. In fact, this is how you do a transitional orbit. If you send something out into space and you put it in a circular orbit close to the Earth, and you want to suddenly go to a higher orbit, this is how you dock with the International Space Station. You go to a circular orbit first, and then you transition to a higher orbit. You do so to make sure everything's okay with the spacecraft before you decide to link it up with a very expensive, very complicated space station. You check the spacecraft out first. Now, you go into a low circular orbit like this, and then when you're prepared to transition and go to a transitional orbit, at the moment you're at position 1, you fire your engines and you speed up so that suddenly you're no longer in that circular orbit and you begin to transition into an elliptical orbit. So you start with the lower circular orbit, fire the engines, and then go into an elliptical orbit. Now you're in an elliptical orbit. When you get out to the place you wish to be, you're not going fast enough to maintain a new circular orbit. So you're going to fall back and you're going to stay in this elliptical orbit unless when you make it to position 2, you fire your engines again to speed up because you have to now get up to speed to be able to maintain the circular orbit. So going from one orbit to another, that transition is complicated. More importantly, it's not complicated in a small way. Remember, you have to time that perfectly so that when you're getting out to your new orbit and increasing your speed, you fire your engines before you make it to the space station because the space station's already out there at that higher orbit. So as you're trying to get out to that orbit and you're in position 3, the space station is probably somewhere out here. And you're both converging on the same spot, but the space station is going faster than you. You're slowing down relative to the space station as you get out there. You need the space station to make it there at the same exact moment that you make it there, but you also have to speed up to stay there, or else you won't be able to link up. It's amazing that they practiced all this for so long. Most people don't know about the Gemini missions at all. They've been kind of forgotten in history. But how many of you know what the Mercury missions were? Okay, a whole two of you. Just a reminder here that two things are happening here at once. First, there's conservation of energy. And conservation of momentum. Both can be used when we talk about this. The reason why energy is conserved is pretty easy. We're dealing with a conservative force. And because we're dealing with a conservative force, energy is moving back and forth between potential energy and kinetic energy. The total energy of our system is just that sum. The amount of kinetic energy. And I'm going to use an S here to recognize we're talking about the mass of the satellite that's moving. And then we're going to have the gravitational potential energy, which normally in the old days we would add, but remember we're going to subtract it here. And that's going to be mass of the satellite, mass of the planet, G, over, and I'm going to put an R here, but that R is changing all the time, just like V is changing all the time. And that's the total energy of the system. The advantage of knowing the energy, or advantage of using energy in this arrangement, is that energy doesn't have any vector properties to it. So in dealing with like how fast are we going at one point compared to how fast we're going at another point, you could use energy to calculate it, but it's the hardest way to do so. I mean, look how complicated that is. And if you're trying to figure out how fast you'd be going at, say, 1 compared to 3, well, you're changing the value of R, but still having to solve this for V. That's a little bit more complicated. I say that because your alternative is to use conservation of momentum. And conservation of momentum does make this easier because there's only 3 things involved with momentum. We're talking about the momentum of a point mass as it goes around the planet. There's R, which is changing all the time, M, which is probably not changing, but V, which is changing all the time, and then the last parameter, the angle. And that's how we calculate the angular momentum of a point mass as it moves from one place to another. But this thing isn't traveling in a circular path, it's traveling in an elliptical path. But because the force is towards the center, there's no external torque on the system. That's why momentum is conserved. Be able to write that down, because that's often asked. Why is the momentum conserved? The energy is conserved because we're dealing with a conservative force. That force is doing work. It's changing the velocity of the spacecraft. So energy is conserved because we're dealing with a conservative force. Momentum is conserved because the direction of that force causes no external torque. Momentum is conserved because the direction of that force, the gravitational force, causes no external torque. Let's consider what that value of R looks like. When we're position 1, I don't want to do that. R looks like this, right? This is the R for position 1. And I want to jump to R for position 2 because obviously it's much larger. And if we look clearly at a comparison between 1 and 2, that should explain to you easily why V min and V max exist. If angular momentum is conserved, when R is small, V is going to have to be big. And when R is big, V is going to have to be small. Dealing with position 1 and 2 is easy because there's a right angle here between R and V, making it easy to deal with angular momentum. That doesn't exist when we start looking at 3 and 4. When we're at 3 and 4, unfortunately, although these two have a similar value for R because of where I placed them, the angle has to be measured here or here. Either one of those will do because we're dealing with the sine function. The sine function is the same in the first 2 quadrants. But you will have to know that angle relative to the tangent. I don't know about you guys, but although I learned about ellipses when I was in high school and a little bit in college, I never learned how to figure out what the direction of the tangent is based on a single point on an ellipse, unless we're talking about point 1 and point 2. I don't know, did you guys learn that? I'm sure it's not being taught in AP Pre-Calc, and I know it wasn't in Pre-Calc Honors either, so that's a toughie. It's not a geometric impossibility, and I think you guys are sharp enough to realize there's probably a way to do that. If you're in calculus, you could take the derivative of the function. That would give you the tangent line. But there's other ways that you can do it geometrically too. Ultimately, what I want to talk to you about here is if you know everything about one place, you should be able to figure out everything about another. You have two conservation rules you can use. And because you have two different conservation rules, one of them is bound to be able to help you. I will say this, ultimately, it is always going to be easier to use momentum than it is to use energy under these circumstances because the momentum function is much simpler. But keep in mind, that ease of use comes at an expense, that you'd have to know the geometrical properties of where you are. So it works great if you're comparing position 1 to position 2. It works less great if you're comparing position 1 to position 3. So if you're doing that, you may have to use energy unless you've been given the angle. The reason why you'd use energy, though, is energy doesn't have direction. So you can use the energy function for any of these locations when comparing any 2 points together. Energy will always work because direction isn't required. But if you have to compare point 1 and 3 and all you have is momentum, it's more challenging for you to work that out because you'll need to figure out that angle. Yep.
On the exam, what would you
It'll look like on the exam. There's about a 1 in 8 chance that they'll ask an orbital question on the exam. They don't ask it very often. So if you look across the 50 years of the exam, orbit questions like this haven't been asked that much, maybe 6-7 times. That's why there's only been there's about 1 in 8 chance. You're going to be asked about orbit somewhere, but it's probably going to be circular orbit and it's probably going to be multiple choice. That's the most likely place for them to place that kind of question. Remember, every single content point will be tested on the exam. It's just whether they're going to place that content in the multiple choice or in the FRQs. So example FRQs from the past. You take a look at the literature and what's been out there. Many of the questions look like this. And that's not an unreasonable expectation. Are you kind of seeing from the picture where they're going to kind of focus you? So obviously this picture is suggesting to you, without even reading what the question is asking, that you're going to be comparing those 2 points where you have a right angle between the velocity and the distance from the planet. And that means you could use angular momentum to figure out your answer. But don't get too complacent. The exam is changing. That's why we need to be prepared for the possibility that they could ask about a different location around there. And you do need to know which of these things is easier to use than the other. So let's try this question. Let's work this one through. It's not particularly hard. And although many of you can't read it, it is in your homework, so I'm sure you could pull it up if you wish. This is FRQ number 1. I do want you to know that FRQ number 5 you can't do. And just hold on to it. It requires some knowledge of simple harmonic motion. So just hold on to it till we cover the next unit because it's going to pop back up when we deal with simple harmonic motion. I'm going to read this out loud to you, and I'm going to write some things down that we're going to need for this. So this problem is a very typical elliptical orbit question. And it says, a spacecraft has a mass of 1,000 kilograms and is in elliptical orbit about the Earth, as shown above. At point A, the spacecraft is at a distance of 1.2 times 10 to the 7th meters and has a velocity of 7.1 times 10 to the 3 meters per second. Now this part is just to make clear what's happening. The velocity is perpendicular to the line connecting the center of the Earth to the spacecraft. So they're being very specific that that's a right angle. It says determine each of the following for the spacecraft, but they also give the mass of the Earth as 6.0 times 10 to the 24th kilograms. And the radius of the Earth as 6.4 times 10 to the 6th meters. Question A and B, I think, are pretty straightforward, and I'm going to leave those to you to do right now. It says, determine the total mechanical energy of the spacecraft, assuming the gravitational potential energy is 0 at an infinite distance from Earth, and the magnitude of the angular momentum of the spacecraft about the center of the Earth. So they're asking you to calculate the energy of that orbit and the angular momentum of that orbit. Did you notice how many words they put in there to talk to you about how to calculate energy? This set of words here. Assuming the gravitational potential energy is 0 at an infinite distance from the Earth. They are telling you to use a specific function. That's what they're saying there. They're saying you can't use MGH. They're telling you specifically to use the gravitational potential energy as measured relative to an infinitely far away point. They will say it like that in the problem. It's a clue. Use the clue that's given. So, I wrote all those things big enough for you to see. You guys calculate the total energy of the system and the angular momentum of the system. So let's consider what you really need here. If you're trying to figure out the energy of the system, remember, it's going to be a little more complicated to calculate. It's 1/2 times the mass of the thing that's moving here, and that's the satellite, times the velocity. They gave you the velocity. Now it's pretty straightforward, but remember, we expect the energy to be negative. So we're going to be subtracting the potential energy, which is the mass of the satellite again, times the mass of the Earth. You do need the constant, and if you haven't memorized it yet, and I can't believe that you haven't memorized something that's 6.67. You say it so often already. But the R that goes here has to be the separation distance between the center of the planet and where the satellite is. So this is going to be the 1.2 times 10 to the 7th meters. Again, this is just plug and chug. It's not particularly interesting. Angular momentum, a little easier, but it's all the same stuff. It's going to be that separation distance, 1.2 times 10 to the 7th. Right? That's that R perpendicular value. Times the mass, 1,000, times the velocity, 7.1, times 10 to the 3rd meters per second. You don't need this, but I'll remind you, they gave it to you so that you would know that the angle here is going to be 90 degrees. This 1.2 times 10 to the 7th, that's in meters. The 1,000 is in kilograms. It's important that you get the units right. You're losing a point if you don't have the units right, maybe 2. So here, kilograms, meters squared per second. This isn't the interesting question because that's just a plug-and-chug kind of question. All of these equations are on the equation sheet. They are not going to give you very many points for this. This is a 15-point FRQ. I believe the average on this particular FRQ was somewhere around 7 out of 15, which means either people couldn't do this, didn't understand how to deal with the energy part, and there will be people who will put MGH in there on the exam. But there's also the fact that there's more interesting questions coming up. So question C is the one I really want you to do, and that's determine the speed of the spacecraft at point B, assuming that point B is 3.6 times 10 to the 7th meters away. So let's see what they're trying to get at here. They're telling you this is 7.3 times 10 to the 6th meters. 6th or 7th? 7th. You have 2 ways to do this because you know the energy here and you know the angular momentum here. You can choose either one to use, but I'm going to be really frank with you. The one you want to use is angular momentum. It is the easiest to use. So give it a shot. We got all the stuff here. In fact, all you need is what's actually on the screen at this moment to figure out how fast it's going at B. So you start by setting the angular momentum at B, which is going to be RB times M times VB, equal to the angular momentum at A, which is RA times M times VA. We can get rid of the angle because we know it's 90 degrees. So super straightforward. And we've already actually calculated this, so you just plug it in there and figure out what the new velocity is. The next question I want you to do, though, and I'm not trying to zip through this. I just know the bell rings in 6 minutes. I know you guys know that. So this one not particularly tough. Talk about the next one. The next one you should do on your own without me, because I don't think it's particularly hard, and it's one we've already done. It says the speed of the spacecraft if it is in a circular orbit around the Earth. They're talking about being at A, and how fast would the spacecraft have to be going at A to be in a circular orbit? We need this number to be able to do part E. So who needs help doing that? You should be honest. Okay, so if it's a circular orbit, that's a specific condition. Write this down, please, so that you don't have to have your hand up next time. Circular orbits have a special condition. The radius is going to stay constant. The velocity is going to be constant because they're traveling in a circle. That condition for a circular orbit is that the gravitational force is providing a centripetal force. So if it says circular orbit, net force equals MAC. That force will be the gravitational force. Write that down so you know. Circular orbit, the only thing acting is going to be gravity. And that's going to be massive satellite, massive planet, G, over the separation distance squared. Remember, this is the force of gravity, so it's got a square in it. That's going to equal the mass of the thing that is doing this circling. So that's going to be the satellite, times v squared over r. R is the radius of curvature, but in this case, it's also the separation distance. Know this. This is going to be on the exam, either through multiple choice or FRQ. They're going to have something about a circular orbit. There's never going to be an elliptical question that doesn't at least at one point see if you can do a circular orbit. Yeah?
You're able to just isolate V if you just cancel everything.
Yeah.
We cancel the R's, right?
One of the R's. Yeah. I mean, we've done this, I know, like dozens of times at this point. But doesn't mean that it's sunk in. Now you work this velocity out. I can't remember what it is, but we need it for the next part, so it's worth me looking and seeing. I think I got 5,700 or 5,000. I think it's 5,800 meters per second. It's question E that's the interesting one, the one that I think people probably didn't get the answer for correctly. And it's one I think we should talk about, at least for the next 2 minutes. What is the minimum speed of the spacecraft at point A if it is to escape completely from the Earth? Now, this is something you will have to have memorized. It's not going to be anywhere on the equation sheet. That the energy at infinity has been selected to be zero. That's how we proved how much potential energy you have when you fall into a gravitational well. So we need the total amount of energy to be brought to zero if you want to escape the gravity of the Earth, which means 1/2 ms v squared minus ms mpg over, this will be RA, because we're starting from A, not the surface of the Earth. We don't want the escape velocity from the Earth. We want the escape velocity from the orbit we're in. We set that equal to 0. So when it's asking for the minimum speed for the spacecraft at point A, the minimum speed brings you to an energy of 0. That's how you can get infinitely far away from the Earth. That's the escape velocity from this orbit. I think a lot of people will put the radius of the Earth here just because that was probably the only time they ever calculated escape velocity. But you can escape from an orbit by just applying the energy when you're in that orbit. Now, we're not going to have time to work this out. This is just solving for V. But if you want to make sure you nail the quiz next week, I would probably do the other FRQs that are here. If we look, there's FRQ, which I think is got a lot in common with what you just did. That's why I put it in there. One for us to do, one for you to do. So I think this would be a nice, maybe if you have a research today, maybe buzz through this a little bit. It's just asking you to do the exact same things we just did. It'll be a good refresher. The difference, they don't give any numbers here, so this is all going to be done symbolically. And then there's another one in there. It's a little more interesting before this one. Take a look at it. There's also